Hi, I'm Makarand Tapaswi, and I will talk to you about our recent work on machine understanding of social situations. Thanks for inviting me to this essay multimedia workshop. We are seeing great successes in recent years in computer vision through deep convolutional neural networks and natural language processing using transformer-based models such as BERT or GPT. Joint understanding of vision and language has also gained a lot of momentum through tasks such as image captioning, where the idea is to describe the content of an image using a short sentence, or video captioning, where given a short video clip, the machine is asked to predict or describe the content, or even visual question answering, where given a question about the content of an image, the machine is trained and learns to answer this question. I see story understanding as the next step in joint understanding of vision and language, and could define it as something like the ability of a machine to watch or read a story and perform some human-like tasks. Some of these tasks include things such as searching or summarizing a storyline, answering questions about events or people in stories, learning about human behavior, which will be the focus of this talk, and hopefully going in the future, even creating new stories. Stories naturally engage both the vision and language components in humans. So to illustrate this, I had given this short paragraph of text to my niece, who was then 6 years old, and asked her if she could come up with a drawing depicting the content of the paragraph. And so this is what she came up with. As you can see, there's a lot of grounding between these two different modalities. There's a fire-breathing dragon, and there are some villagers who go to their queen and ask for help. So even a 6-year-old is able to do this, while our models and machines struggle quite a bit while doing this right now. We all love stories. There's this famous video clip on YouTube that kind of depicts this in a really nice way.
In the summer, I like to lie in the sun and watch the birds. And I like to watch the frogs in the pond. Then I curl up in my hollow tree and dream about spring. The end.
And this clip continues. So every time the mom basically stops reading the book and kind of closes it and says the end, the baby starts crying. And this is basically an illustration of how much we would like to listen to stories. And this continues even as adults, resulting in things like binge watching. So coming back towards understanding human behavior from stories, while collecting data of human behavior in general in the society is quite hard and has several privacy implications. If you're the Batman, you could turn every phone in the city into a transceiver and get some data, but we probably don't want to go through this approach. What we do instead is to use movies as a proxy to real-world scenarios. We observe that movies often depict social situations that one might encounter in their daily lives, and we want to capture the essence of these situations depicted in such movies. In this talk, I would like to focus on two aspects of building socially intelligent AI. In the first part, we'll look at this thing called MovieGraphs, where we try to capture this essence of movies, social situations in movies in a graph. And in the second part, we'll look at a joint study on learning about interactions and relationships between pairs of people in movies. So let's start with the first one. Back in 2016, we had this idea of creating a story question answering benchmark based on movies. So what we did was we took a long movie and created a bunch of questions along with 5 multiple choice options. And these questions were fairly complicated, ranging from who did what to whom, but also why and how. So for example, in this question shown here, you can see that we are kind of trying to infer why does Cypher betray Morpheus? And if you watch the movie, then you have this notion of understanding what Cypher is going through, why he would rather be part of the Matrix than be in the real world. Doing this obviously is quite hard for machines, as they need to analyze over hundreds of thousands of frames, a lot of dialogues, and even long-range temporal dependencies between actions and emotions and intentions of characters. So to kind of get a better hold or a better understanding of human behavior, instead of going through the question answering route, we thought of being a bit more explicit and creating some annotations or collecting some data in this regard. In particular, we looked at movies and divided them into different clips, each containing a self-contained social situation. And for each clip, then we annotated a graph containing a variety of aspects of human behavior. So what are some of the aspects that we kind of included in our annotations? The first thing that we had was this overarching situation label, which kind of describes what is the content or what is the intention of this particular scene. Clips range around 45 seconds to 1 minute, and they show things such as a wedding or an introduction or an argument, for example. We have a bunch of interactions between pairs of characters, both visual as well as based on dialogue. We have relationships, both family and social relationships, as well as annotate a bunch of attributes, including physical attributes such as age and gender, but also emotional attributes such as nervous, quiet, and upset in this case. So what are movie graphs? Let's look at this video clip from Forrest Gump and get a better understanding of these annotations.
Hey, dummy! Are you proud of just plain Snoop Dogg? I'm Forrest Gump. Just run away, Forrest. Run, Forrest! Run away! Hurry! Get the brakes! Hurry up, let's get it!
So as we can see from this video clip, we can say that the situation is probably bullying. We also label where this situation happens, in this case from the Places 365 dataset, and also a short description of 2-3 sentences for this long video clip. Finally, we start annotating the graph by first creating the bunch of characters that appear in this clip, annotating their emotions or attributes in general. So in this case, we see that Forrest is scared and frustrated, while Jenny is compassionate, while the bullies are hateful and violent. We then start annotating the interactions. Here we see that the bullies hit Forrest, and then topic nodes, yellow nodes, kind of describe this interaction in more detail, such as bullies hit Forrest with rocks, or bullies insult Forrest that he's a dummy. We also have purple nodes that kind of reason about why the bullies may have done so, and in this case they insult him because he's different from them. Based on these interactions, we could infer that the relationship between the bullies and Forrest is that of an enemy. Then Jenny encourages Forrest to run, and Forrest runs from the bullies. Note that these arrows are directed, indicating the direction of the interaction. We also include timestamp nodes shown in gray squares to kind of ground these interactions in the video clip to say during what period of time does this interaction happen. Characters are grounded in the movie through person identification. So by aggregating a lot of information about all these annotations across 50 movies and about 7,600 clips, we can explore a lot of social common sense. By looking at, for example, interactions versus situations, we can see some interesting information, such as at a party, people dance with each other, or at a robbery, people threaten each other or yell at each other. At an escape scene, there is some hitting, and hopefully, based on some bias from movies, of course, at a wedding, the couple agrees. Note that our annotations are across time, and we have annotations essentially for almost every clip in the movie that contains a social situation. Thus, we can kind of create this flow graph of how situations evolve from each other. For example, if we start at a date, this could be followed by an intimacy scene, followed by waking up, and followed by breakfast. Alternatively, this could be also, after intimacy, could be going to work and then planning some events. So we have also looked into kind of creating new storylines based on sampling of these situation flows. I'll briefly talk about a few tasks that we have worked on using these movie graphs. One of the core ideas was to use graph-based clip retrieval. So imagine that you want to search for a specific video clip, and you're looking, for example, in this case, for two people who are talking about their relationship at a church. And you can see that one of them is a male, the other one is a female, and they are regretful and confused. So we can label a bunch of emotions or interactions or any subset of the information that we have in our annotations and kind of search for this event happening across several movies. And so this is what we get for our rank 1 and rank 2 clips. We see that rank 2 is the correct actual clip that we were looking for, while rank 1 happens to be a very related clip where you see a couple talking about arguing in this case, and they are quite heartbroken and remorseful, so related to the emotions that you're looking for in the query. Note that since we are agnostic about the names of the characters, these two clips even come from different movies. Another task that we looked at was reason prediction, where the idea was to use encoder-decoder framework to kind of combine information from such as a pair of characters, a male and a female, who are related by the spouse, so they are married to each other, and at a house they are talking about adoption. So the interaction is that they embrace, and then a model is basically given all this information and asked to predict why do they embrace. So the prediction in this case is that he is scared, which is very plausible reason about while talking about adoption, while the ground truth in this particular example happens to be that they are glad that he'll have a baby. So this kind of goes to show that our model is able to reason to some extent just based on the information provided in the graph, and perhaps by looking at the video clip in more detail, we'll even be able to get to the point where we can reason about why people are interacting in the way they are. Another aspect that we looked at was something called interaction ordering. The idea was to mainly look at interactions between a pair of characters, removing out all the other pieces of information, and then say that if Forrest runs from the bullies, bullies hit Forrest with rocks, and bullies insult that he's dummy. These are a bunch of interactions that happen in this clip. However, they often happen sequentially in the clip, and if you can say what is the order of these interactions, that might allow the models to reason about causality or how interactions evolve over time. So we took an LSTM model and were able to kind of generate the ordered set of interactions based on these clips. This is often, again, another subjective task, which is not necessarily always trivial to do, even for humans, but a model showed quite good performance in this task as well. So a second aspect that we were interested in is joint learning of interactions and relationships. This is more recent work from CVPR. And the idea here is that given a video clip, for example, and a bunch of interactions, we could kind of infer the relationship between a pair of people based on their interactions. For example, if there are a bunch of people who are laughing or helping or eating with each other, they might most likely be friends. Alternatively, relationships even often drive interactions. For example, top-down relationships such as teacher-student can drive interactions such as teacher teaches something or teacher consoles the student or maybe asks the student some questions. So we're kind of interested in analyzing whether we can learn about interactions and relationships jointly so as to get a better understanding of the situation as a whole. We develop a multimodal embedding model that takes in the visual information from the clip, uses standard encoding methods such as I3D, which is a 3D convolutional network, text all the dialogue in the clip encoded through BERT, a transformer-based natural language model. And we also focus on the directionality of characters that we talked about in the previous examples, where we're now interested in finding the interaction or relationship between character 1 to character 2. So we encode the visual appearance of the people as well and combine these as a stack vector. We look at interaction prediction based on these multiple modalities. Given the visual clip only, our model predicts that these two people are either walking away from each other or looking at each other, watching each other. While combining them with textual information, which in this case is actually no dialogue between these two characters, our model switches its prediction to leaves, which is plausible considering when two people leave each other, they probably don't talk with each other. Furthermore, combining information or the visual appearance of these two characters by looking at them in detail, a model is more confident about the interaction being leaves. We now look at joint predictions of interactions relationships and kind of can we learn them together. So in the simple case, we had feature vector for one interaction fed to a normal classifier. For relationships, we noticed that relationships in movies often last for a longer period of time, and therefore we could combine the information from several clips, in this case about 6 to 20, and average pool them and learn a classifier on these averaged representations, which led to better performance. Additionally, we also noticed that by feeding the relationship information and making the interaction depend on both the relationship and interaction feature itself, we obtained better predictions for both interactions and relationships on average. So in this case, our model is able to correctly predict the interaction asks and the relationship frame. If you look at the numbers, the performance improvement, however, is quite modest. But looking deeper, we notice that some interactions that have specific relationships, such as hugs, is typically limited to a few relationships, while these see a large improvement in performance, even up to 15 or 17%, while generic interactions based on dialogues that happen between all relationships almost see a slight drop in performance. A similar pattern is seen for relationships, where relationships that have unique interactions see a large gain in performance, while relationships that are relatively common or include interactions that are fairly common across all relationships see a small drop. A third thing that we wanted to predict in this case was also which pair of characters are involved. So given a clip, we would even ignore the fact that we don't know which pair of characters exist and how they are related. We call this training with weak clip level labels, and we treat the character pair as a latent variable and use some tricks such as hard negative sampling to estimate them. Essentially what we have is a 3D tensor where we are given a bunch of relationships, a bunch of interactions, and all possible character pairs in this particular clip. So we can predict who is interacting, or given the interaction relationship, or what is the relationship given the character and interaction, or what are they doing given the character and the relationship, by slicing the different aspects of this tensor. So to look at this explicitly, we can see an example where we're given a clip along with the dialogue. In this case, there are 3 characters, so we'll have 6 track pairs in directed form, and their corresponding relationships are shown at the right. We now have different aspects. Given the relationship parent and the interaction talks to, we can predict who the pair of characters are. Again, note that this is directed, so it needs to be that the father and the child comes later. Given the pair of characters and the relationship, we can predict what they're doing. Given the pair of characters and what their interaction, we can predict their relationship. Or finally, if we're given nothing, we can try and predict everything. So obviously this is a very complicated task, and accuracies for joint prediction are around 2% or 2.5%. But an interesting factor is that even with weak clip level labels, we're able to achieve this performance up to 1.5% quite nicely. So in conclusion, I would like to say that social situations are quite tricky, and we need to be careful about how we build our machine learning models. This cartoon, for example, shows this very nicely, where I am sorry and my bad generally mean the same thing, but not everywhere. I would like to thank all my collaborators. It's been a great time working both at the University of Toronto on these projects and then continuing this with Anna at INRIA. And thank you for listening to this talk. If there are any questions, please feel free to email me, or we can even take them during the discussion session later. Thank you.